Hi, welcome to 26th session on measure theory. This is the ninth session on Lebesgue integral. Today we will be talking about the fundamental theorem of calculus. Okay. Notice that technically we have already showed that any Riemann integral function is measurable and Lebesgue integrable, and the Lebesgue integral equal to the Riemann integral. And hence whatever you have done in Riemann theory, fundamental theorem of calculus, etc., will be valid. But I would like to quickly go through that proof, okay? Because on the way, one of the important concepts is the indefinite integral, okay? So there are some interesting facts about indefinite integral. We will define it, and that should be worth noting. And in fact, one of the very famous results of Lebesgue characterizes when a function is indefinite integral. Okay, we will not get into that. Okay, but the point I want to say is it's one of the most significant achievements of Lebesgue theory. So at least we will start doing such things. So in this lecture, the main deal is the question of indefinite integral. Sometimes it doesn't move indefinite integral. What does it mean? Suppose I have a function f in L1, let us say of R or L1 of some interval a b. Okay, all are with respect to the Lebesgue measure. Okay, and this L1 is my script L1. Even though for easy of simple writing, I will write a little this L instead of script L. It takes time. Indefinite integral. This is D. Okay, how is it defined? We define, for example, in this case, g of x to be minus infinity to x f dm. Okay, this again, let me write it, minus infinity to x, open or interval, doesn't matter, of f dm. Okay, this is a measurable set, f is L1, therefore this simply means integral of f indicate a function of minus infinity to x dm over r, right? So this, and in the case when f belongs to your L1 of AB, which is the most often that's the case we may look at, again g of x, since we have starting point, we will start with that. Again, this is, I am writing this as a human notation, f of m dm. A of x. This is called, g is called the indefinite. I say an indefinite because suppose it's a p, I could have started with c also, c to x. Okay, x may be somewhere here or here. Okay, still it will make sense. Okay, right. The first thing we want to prove is the following. Let f be in L1 of R or in L1 of AB. I will simply write L1, okay? It will be easier from the context, okay? Then I want to say my g of x, the indefinite, maybe I have to say that here. Let us say a of x. Let me write ax to f dm. Okay, this is a function from g from AB to R. This is continuous. Notice that this is well defined because this is integral of f I Ax, and therefore the modulus of this is less than or equal to integral of mod f, and hence this over AB is less than or equal to this over AB, which is finite. Therefore this is integrable, and hence this integral makes sense. Okay, pause, review. Okay, so g is a function, a real valued function from, let us say, AB to R, or maybe from R to R also. In that case, I will have a minus infinity to something. So what I want to show is g is continuous. Even if it is R to R, right? So this is you might have seen it in theory of Riemann integral, but the reason why I want to do it to illustrate the power of dominated convergence theorem, and also something what you had already done. Okay, let us first prove this is continuous, right? So let us say fix a point x in AB. Okay, this x may be equal to a, x may be equal to b, etc. Let Tn be a sequence in AB such that Tn converges to x. So I have to prove g of Tn converges to g of x, right? Okay. Now notice that g of Tn by definition is integral whatever it is minus infinity or something here to Tn, okay, of f dm, right? But this is nothing other than, as I said, integral of f into a Tn dm over the AB. Maybe over R also, in that case is minus infinity. Okay, let us stick to f in L1 of AB. Okay, other cases similar, you can put that. This is dm, right? Now notice that this one Atn converges to, where does it converge to? As Tn goes to, as n goes to infinity, that is Tn goes to a, this goes to f of this singleton a, which is 0. Yeah, sorry, I think I'm making a mistake. Integral f of I of a Tn minus integral of f of I of a x. X is there, right? Tn converges to x. That's where I made the mistake. Okay, I was just wondering. So f integral I of a Tn converges to point was a of x. That means this function f integral I of a Tn minus f integral I of the integrated function of a of x goes to 0 pointwise, right? Okay. And the next thing you should notice is the integral of a of Tn, as I said, is less than or equal to integral of f, sorry, mod f, and hence this is integrable, and this one converges to f of I of a Tn converges to f of I of ax pointwise. Therefore, I can use dominated convergence theorem, because these are all, call this as fn's or something, fn's are dominated by f, right? It converges to this function. Therefore, by dominated convergence theorem, integral of f and a Tn converge to integral of f I ax. But this is nothing other than g of x and g of Tn. This is nothing other than g of x. Therefore, g of Tn converges to g of x. Hence, g is continuous at So pause, review, proceed. Alright, you see that how we used a dominated convergence theorem to do that. I am going to actually prove the indefinite integral G is uniformly continuous. Okay, yeah, that's a stronger statement. Even if f is in L1 of R, not necessarily you may think, okay, if it is continuous on the closed and boundary AB, it will be automatically uniformly continuous. Is that right? If any continuous function on a closed and bounded interval or any compact metric space is uniformly continuous. So there is nothing new. But what we are trying to do is, if even if f is an unbounded interval or f is in L1 in R, then also the statement is true. Okay, how are we going to prove that? Okay, so to just make sure, let us assume this L1 of R. Okay, and g of x equal to minus infinity to x of f dm, then g is uniformly continuous. G is from R to R is uniformly continuous. As defined earlier, remember g of x makes sense, it's an R because this is integrable. Okay, this is nothing other than integral of f minus infinity to x in modulus is less than or equal to mod f, and that is in L1, etc. Therefore, this integrable, therefore this exists as a real number. Okay, therefore g is a function from R to R, uniformly continuous. So the proof is easy. Remember, we proved the absolute continuity of the integral. What does it say? It said that if x b mu is a measure space and f is in L1 of x, b mu, right? For every epsilon greater than 0, there is a delta positive, so that if E belongs for every E in B, so that mu of E is less than delta, we have integral of mod f over E will be less than epsilon. Okay, right? We proved it. Go through the proof. This was proved after DCT and plus truncation. That is, do you remember fn of x we defined to be fx if mod fx is less than or equal to n, otherwise equal to n. Okay. Okay, and we said that, okay, this one converges to fx pointwise by dominated convergence theorem, it converges, etc., etc. Please go through the proof, recall that, because many people may not think it's a good thing, but it's a very, very powerful result. We are going to use that. Okay, now, so I will let x belong to x and y both belong to AB, right? Then I want to estimate gx minus gy. Remember, uniform continuity means there is no fixed point. Take any 2 points, then you have to estimate gx minus gy to prove uniform continuity. This fellow is going to be integral over either xy if x is less than or equal to y, or yx. Okay, of f dm. Why? Because gx is, so minus infinity to x, yeah, and g of y is f minus infinity to y dm, right? So there are two possibilities, x and y may be like this, or other way around, y and x may be like this, right? Therefore this, and remember f is L1, right? And we know it's as a set function, it's additive, that is integral of f over a, right, union b equal to integral of f over a plus integral of f over b. This is d with respect to any measure. If a and b are measurable and a intersection b is empty, right? Therefore, if x is less than or equal to y, then minus infinity x minus infinity y I can write as minus infinity to x union xy, or the other way around, minus infinity. If x is greater than or equal to y, then minus infinity of x will be minus infinity of y union y x, right? Therefore, you can see, let us assume the first case, okay, x. Therefore, my g of y, I can write it as minus infinity to x f dm plus f dm over x to y, right? But this fellow is nothing other than g of x. Therefore, g of y minus g of x in modulus equal to modulus of integral f dm over x y, right? But that is less than or equal to integral of mod f over dm over the interval x y, right? Now let's use the, suppose I wanted to prove g is uniformly continuous, let epsilon greater than be given, right? For this epsilon, because of absolute continuity of the integral, okay, there is a delta positive, so that whenever mu m of e is less than delta, e belong to Lebesgue immutable set, the integral of mod f over e dm is less than epsilon. Therefore, whenever mod x minus y is less than delta, then this will be less than epsilon. So we have proved this uniformly continuous. So you see that we have used absolute continuity of the integral, right, to prove that. Okay, these are the first result. Please go through, and both the proofs I tried to make use of measure theory to give the proof. Okay, right. Whereas in the Riemann integral, you would have assumed f is bounded, Riemann integrable. Therefore, g of x equal to a t x f of t dt. Therefore, you know that it is less than or equal to m times modulus will be bounded by m times b minus a. Such things you have to use there. Okay. So here we avoided because f need not even be bounded and the domain need not be bounded. We saw the proof. So we have to use some convergence theorem, right? So please go through the proof to understand that. The next thing we want to prove is the indefinite integral is a function of bounded variation. Okay, I will recall the definition. Okay, then we will go through the proof. Okay, right. The next thing is a function f from interval a b to r, this is close to, is of bounded variation. Okay, we have to define. Okay, but let me first motivate how I define this. The reason is, let's look at f from a b to r. Assume for the time it is non-negative, so that I can draw the picture like this. Right, now this is my a, this is my b. So I want to, I think of this as a curve, x fx. This is a curve in R2. It's a parameterized curve. Okay, that is x going to x comma fx. That's a curve, right? Now I want to find the arc length. Okay, how do I find that? As usual, what you do is you split it into various small parts. Okay, partition this and look at their thing. Okay, now look at this and this. Look at the line segment. Look at this. Look at the line segment and look at this. Look at this line segment and look at this. Look at the line segment. Look at this. Look at the line segment. Look at this. Look at the line segment. Look at this. So some of these lengths, okay, right, they constitute an approximation to the length of the curve. Do you understand why? Because this point here is what this will be. Let us say this is x1. This will be x1 fx1. Therefore, the length here, this is x naught, fx naught. Therefore, what is the distance between these 2 points? X naught, fx naught, and x1, fx1. Okay. So you can see this is going to be in some sense dominated by this thing. Okay. Right. This will be governed by mod x1 minus x0 plus mod fx1 minus fx0. Okay. If I do all such things, okay, x1 to x2, x2 to x3, xn minus 1 to xn, etc. So what I will have will be these fellows. Mod xk minus 1 k equal to 1 to n plus the same thing mod fx k minus fx k1 k minus 1 k equal to 1 to n. Notice that this will be nothing other than b minus a. This is always finite. Therefore, whether the okay, as I keep increasing the partition, okay, as partition varies, okay, let us look at this, the approximate length. Okay, approximate length, let me write length of the graph of f with respect to the partition. Okay, this is determined by this because this is always bounded, right? Therefore, if I look at supremum of this length of the graph of f with respect to various partitions, okay, it has to be bounded, but this will always be bounded. Therefore, the boundedness comes from here, right? Okay, so just pause, review, proceed. I gave this only as a motivation, okay, so that now you know why I wanted to find. So let p equal to x not equal to a less than x1 less than xn equal to b be a partition of ab. Okay, then the variation of f with respect to the partition p is defined by what we did earlier, variation of f p. This by definition is summation mod f of xk minus f of sk minus 1, where k is k, okay, x naught to xn are the nodes of the partition p. Okay, and I say f is a bounded variation definition. Here supremum of the set v of p as p partition varies over the partitions of AB is finite. So roughly this means this graph will have a length. Okay, this is the basic idea. Is it okay? So pause, review, proceed. So now what we want to prove is the second statement. Let f belong to L1 of AB. Now I am restricted to finite intervals. Then define the indefinite g of x to be a to x f dm. Then g is a bounded variation on AB because it's a function defined only on AB, right? Okay, this is called the total variation, but we are not going to use the word now. Okay, this is what we want to prove. So what is that? So I am starting with the partition a equal to x naught less than x1 less than xn less than b. right? So I have to look at the variation of the partition of G, sorry, G. What is this by definition? This is G of xk minus G of xk minus 1, k equal to 1 to n modulus. Yeah. Now what is the, remember xk minus 1, therefore G of xk minus G of xk minus 1, as you have seen earlier, is nothing other than integral of f over sk minus 1 to xk of f dm. Okay, as seen earlier. Because this will be integral of f into I of axk and minus integral of f into I of axk minus 1. Now you use the additivity of the integral, okay, and to check, show that these are equal to this, okay, as seen earlier, right? Therefore, modulus of g of xk minus g of xk minus 1 is, okay, this is what I want to look at, yeah? But that will be less than or equal to integral of mod f dm over sk minus 1 xk, right? And hence the summation variation of g with respect to partition p by definition is the summation g of xk minus g of sk minus 1 k equal to 1 to n will be less than or equal to summation k equal to 1 to n or integral of mod f dm over xk minus 1 to xk. But this, again by additivity of the integral, remember we have proved that integral is even countable additive, in particular it's additive, finite additive. This is nothing other than integral of, is equal to actually by definition integral of AB of mod f dm. Okay. Therefore, we had actually proved the total variation, which is LUB of finite variations with respect to the partition P of AB. Each one of them is less than equal to this, therefore it's less than equal to mod f over AB. Okay. Hence, G is, this is G, sorry, mod G, mod f. Total variation of G on AB, V of GP, but V of GP is, we have seen that less than equal to integral of mod f over the interval, therefore we have proved. Variation. The power is running out. Let me switch on the power. So, what are the things we have proved now? If f is in L1 over R or interval on R, then we have proved f is continuous, in fact it is uniformly continuous. Second result we have proved is that if f is in L1 over a finite interval, then it is of bounded variation. The third thing what we want to prove is it is absolutely continuous. So again I will make a definition and we will prove it. Okay. Right. So let f be a function from interval a b to r is absolutely continuous okay if for any given epsilon positive there is a delta positive, so that if jk equal to some, let us say xi yi x okay, gi for 1 less than equal to I less than equal to k. B pairwise disjoint intervals in the interval AB such that the total length of ji equal to 1 to n 1 to k, that is modulus of yi minus xi summation I equal to 1 to k, that is less than epsilon. Implies, okay, we want to say g of something, g of yi minus g of xi summation and modulus I equal to 1 to k, that is less than epsilon. See that? Actually, I was struggling to write down the definition, but I simply recalled absolute continuity of the integral and tried to write that. Okay. Yeah? Did you understand that? Forget f there, use g, that's all it says. Yeah? What do I want to say? G. The integral is absolutely continuous, that means integral of mod f over f e will be less than epsilon whenever mu of e is less than delta, right? Given epsilon, there is a delta with this property. So you gave me an epsilon. So I wanted to say g my f is absolutely continuous. So we just try to write down the definition. Okay, g is absolutely continuous. That's what we want to write. Okay, right. Let us go through it. So let us prove it. Okay, this follows from absolute continuity. Right. Okay, this I am writing g. Okay, g is absolutely continuous if for any given epsilon greater than 0 there is a delta, so that if I have a finite sequence of pairwise disjoint intervals whose total length is less than delta, the sum of these fellows modulus of gyi minus gxi is less than epsilon. Is that clear? But this is a automatic. In fact, I got the definition by recalling the absolute continuity of the integral. So let f be in L1 of AB and define g of x as usual, integral a to x of f dm, then g is absolutely continuous on AB. Right? Okay, what does it mean? So you are going to give me a collection ji, which is, let us say xi yi, I 1 less than equal to I less than equal to k, and ji are pairwise disjoint. Right? Okay, you gave me epsilon positive. Right? Okay, then what I know is let delta correspond to the given epsilon using the absolute continuity of the integral. What do I mean by that? What I mean is, okay, for this epsilon, since the integral is absolutely continuous, that means for this epsilon there exists a delta positive, so that for every measurable set E in the interval AB, okay, contained in AB, and E is measurable with measure of E less than delta, should imply integral of G over E or integral of mod G over E should be less than epsilon. Is that okay? Right? So this delta is what I am looking at. So now assume that these are all let this be a pairwise disjoint collection, finite collection, so that modulus of length of ji is less than delta. Then what is it I have to prove? I have to prove modulus of g of yi minus g of xi I equal to 1 to k is less than epsilon. Right? But what is this? notice that g of x, what is g of yi? G of yi is integral of f over the a of yi, and g of xi is integral of f over a of xi dm. Therefore, g of yi minus g of xi g of yi minus g of xi is integral of f over xi to yi. This again as seen earlier, right? Therefore, modulus will be less than or equal to modulus. Okay, right? Therefore, the summation of mod g of yi minus g of xi I equal to 1 to k will be less than or equal to summation over I equal to 1 to k of integral mod xi yi mod f dm. Right? Since these are pairwise disjoint, this is nothing other than integral of mod f over the union of xi yi. I equal to 1 to k. Right? Because remember, if a and b are disjoint, okay, the union, okay, this will be I of a union. We had already seen it. I am using that, right? But what is the total measure of this set? Measure of this set union of xi yi, because the pairwise disjoint is less than or equal to yi minus xi, but that one equal to 1 to k, but that's less than delta. Therefore, by absolute continuity, this is less than epsilon. Yeah. So go through these proofs. Indefinite integral is one of the important tricks. Okay. So what you have done is, if f is an L1, the indefinite integral is uniformly continuous, and second it is a bounded variation, and third it is absolutely continuous. Okay, these are the three important results we have proved about uniform continuity. The next result is the so-called fundamental theorem of calculus. Suppose, let us assume f is in L1 of AB and f is continuous at x, at a c, let us say at c point, a point in AB, right? Then I have a function anyway g, the indefinite g of x. Then what we want to prove is g is differentiable at c, and the derivative of g at c, that is g dash c, equal to f of c. This is the fundamental theorem of calculus. We want to prove that. Is the statement clear? I will write it in a minute. Good. I still have time, so let us do that. So, fundamental theorem of calculus. Let f be in L1 of AB. Let f be continuous at C in AB. Okay, it may even be the endpoints, okay, but I will pretend that C is in the open interval AB, okay, but whatever you are going to say will be correct, okay. Define g of x to be integral of a to x f dm, then we know g is continuous, actually uniformly continuous, then g is differentiable at C, and g dash c is f at c. Yeah, right. So this is the fundamental theorem of calculus. This is known as fundamental theorem of calculus. This is at least one version. There are two versions perhaps. I do not know which one is one and two, etc. But this is for me, this is the first version. Very important one. Okay, right. So let us try to prove that. So So let us C and H be said that. Okay. Let us assume H is positive to start with. C plus H belong to AB. Therefore, G of C plus H minus G of C by H. I want to say limit exists as H goes to 0 and equal to F dash. Sorry, equal to F of C. Okay. H could be H is not equal to 0, H be positive or H is negative. Okay. Right. Now what is G of C plus H minus G? So let us look at that. We have seen that G of C plus H minus G of C, we had already seen many times. It is C to C plus H FDM. Right. Now this is where I want C to C plus H is C to C plus H if H is positive, otherwise C plus H to C if H is negative. Okay, this is just a notation. You understand that? Yeah. Right. So that's why let us assume H is positive so that you will have no problem. Okay. Then what do I want to do? I want to say G of C plus H minus G of C by H. Okay, I want to estimate that's FC. This I want to say is less than epsilon. Given epsilon, there is a delta positive, so that for all H, 0 less than mod H less than delta, this minus this is less than epsilon. That would mean the limit of G of C plus H minus G of C by H as H goes to 0 exists and it is equal to FC. Okay, but the limit is G dash C and G dash C equal to FC will follow. Is it clear? This all. The important trick in fundamental theorem of calculus is F of C. Notice that this fellow is nothing other than this fellow. Okay, this guy is 1 by H and integral C to C plus H of FD. Right? Now this is just FC is a constant. So what I do is FC, I write it as again integral C to C plus H of FC. Okay. Now what is the length of this interval? Length of the interval is mod H. Right? Because this will be FC into length of the interval mod H. Therefore I will write F of C as 1 by mod H time F of C over the interval C to C plus H. Remember, C to C plus H is within quotes. If H is positive, it is that. Is that clear? Therefore, whatever I have written here is going to be 1 by H integral of F of C, C to C plus H. Is that clear? There is also modulus, etc. Mod H here. Right? Okay. Therefore, this one I can write this as F of T minus F of C by C to C plus H dm of T. Remember my notation? If whenever I want the variable to be seen, I will like it because here it's a constant. Right? So this will be less than or equal to modulus here and 1 by mod H is outside. Right? Now since F is continuous at C, therefore for the given epsilon there is a delta positive, so that mod T minus C is less than delta should imply mod Ft minus Fc will be less than epsilon. Therefore I can assume my T is so that mod T minus is less than delta. Right? Therefore for T in C minus delta to C plus delta, what we have is this. This will be less than or equal to 1 by mod H into less than epsilon on the interval C to C plus H dmt. This is again the interval. Therefore, that is equal to 1 by mod H into epsilon into the length of the interval mod H, which is equal to epsilon. Yeah, go through the proof. Therefore, we have shown G is differentiable at C and G dash C is FC. The next fundamental theorem of calculus, second version or second. Two says, suppose my f equal to g dash and g is continuously differentiable. That means g dash is continuous. G dash exists, it is continuous on AB. Right? Then f equal to g dash is continuous, therefore it's a Riemann integral and hence it's a Lebesgue integral. Is that clear, right? Then what you want to say is integral of a to b f dm is nothing other than g of b minus g of a. Notice that this is nothing other than integral a to b of fx dx, Riemann integral. Is that clear? Okay. Right? So how does it follow? So what we do is you define f of x to be integral a to x of f of t dmt. Right? I want, is that okay? Maybe I want a g, let me just see. What do I want? I want to say that, okay? Yeah. Now, so notice that f is g dash and this is continuous. Therefore, we know f is differential and f dash of x equal to f of x for all x in AB. Right? But notice that g dash x is also f of x for all x. Right? And therefore, the function f dash minus g dash is 0. That is f minus g dash is 0 on AB. That means f minus g must be constant. We are using the interval here on AB, right? That means f of b minus g of b must be equal to f of a minus g of a. But f of b is what? Integral a to b of f dm minus g of b equal to f of a is 0 because it is integral from a to a of f, that is 0 minus g of a. Therefore, integral f dm over integral ab is g of this is g of b minus g of a. So we proved. Okay, pause, review. So now we are at liberty. So whenever we have some function whose Riemann integral exists, etc., and if it admits a primitive, this g is called a primitive, right? If f equal to g dash, g is called a primitive of f. Okay, we can use the second version of fundamental theorem of calculus to compute the integral, right? So how do we do that? Okay, I'll give an example. Okay, with that we will stop. So let p be positive. Okay, let us look at the interval 0, 1 or 0, 1. Look at the function f of x equal to x power b. Okay, this is continuous, right? No, let p be in R. Okay, x be continuous. Okay, on notice that this one, but it's unbounded. Unbounded if p is negative, right? If p is negative, it will be 1 by x power minus p, and as x goes to the 0, it will be unbounded on the interval. The problem is at near 0. I want to know whether f belongs to L1 of 0, 1. L. Okay. So what I do is, see, now I can't use Riemann integral straight away. If you want, you can even assume this one closed. Okay. Right. I want to know this. And notice that whether f belongs to L1 of 0 1 also doesn't matter, because I can define the function f at 0 to be 0, because that will be f will be measurable, and if this f is measurable here, it will be measurable here. Okay, are you following? I can, even though I'm looking at functions here, okay, I can think of these functions here in the Lebesgue theory by defining f at 0 to be 0. Even though limit x goes to 0 of f may not exist, if p is 0, p is less than 0, I don't have to worry about it. Okay, come back to this. So I want to have f at 0 1. Okay, now I cannot apply because this is unbounded function, therefore Riemann integral doesn't exist. The fundamental theorem of calculus, etc., cannot be applied because on 0 1 f is not defined. Even if I assume here, then I want it to closed and bounded interval, etc. So the trick is, you look at only this interval 1 by n to 1, right? Now on that I have a primitive. xp has a primitive, namely xp plus 1 by p plus 1 if p plus 1 is not equal to 0, right? Derivative of this will be this, right? So let us assume p plus 1 is not equal to 0. Then what do I have? I have integral 1 by n. Now let me write the ordinary Riemann integral, because they are one and the same. X power p dx is nothing other than x power p plus 1 by p plus 1, which is 1 by p plus 1. And this is add to 1 and minus 1 by, this will be 1 by n plus p plus 1. You understand that? And notice that if I define fn to be f into 1 by n1, okay, then fn increases to my f on 0 1, and they are all non-negative, right? Therefore monotone convergence theorem is applicable. Therefore fn increases to f, right? Therefore by MCT, okay, integral f is a limit of integral fn. Okay, what is integral of fn? That I already know. This is, therefore this is going to be limit of over n of 1 minus 1 by n to the power p plus 1. Okay, so you can see if p plus 1 is positive, okay, then this is limit is 1. Therefore f belong to L1 of 0 1 if p plus 1 is positive. Yeah. So what is the significance of this result? You can see we cannot deal with x power p on the open at 0, closed at 1 interval by our Riemann integration, because, okay, I want the interval to be finite and bounded and closed. Yeah, even if p plus 1 is positive, x power p may, okay, there will be problem, because if p is less than 0, p plus 1 is 0, that means p must be greater than minus 1. So if p equal to minus half, you can see the function is unbounded. So I can't talk about Riemann integral. So the way we dealt with was truncating the domain to 1 by n to 1 and applying fundamental theorem of calculus there, and applying monotone convergence theorem to show that x power p is integrable. Yeah. But let us contrast with the next one. Now let's look at the same function f of x equal to x power p. P is not. Okay. And now the interval is 1 to infinity. Right? Again, as we did earlier, if p plus 1 is not equal to 0, it has a primitive x p power 1 by p plus 1. Right? Now again I can use Riemann integral only to 1 to n of f x power p. That will be x power p plus 1 by p plus 1, which is 1 by p plus 1, 1 minus 1 by n to the power p plus 1. You understand that? So now you can see if p plus 1 is negative, okay, then limit of 1 to n or x power p equal to limit n tends to infinity of 1 by p plus 1 to 1 minus 1 to the n to the power p plus 1 exists and is equal to 1 by p plus 1. Because this goes to 0 if p plus 1 is negative. Therefore, x power p belongs to L1 of 1 infinity if p plus 1 is negative, and x power p belongs to L1 of 0, 1 if p plus 1 is positive. See, contrast this. Again, notice that we used monotone convergence theorem here. The way I used here, I also use this here. Here define f1 to be f into 1 to n, right? Then f1 increases to f, and I can use monotone convergence theorem. Integral of f1 converges to integral of f. Integral of fn we know, therefore the limit is what you have to look at. Okay. So this is a very useful result. Okay, many times I find that people go through a lot of measure theory, etc. When I asked when is x power p belong to integrable near 0 or near infinity, they have no idea. Yeah, please go through this example. Okay, and in the next session, if there is time permits, I will go through 1 or 2 examples to illustrate how to use this fundamental theorem of calculus and various convergence theorems to evaluate integrals or estimate integrals or to find the limit of a sequence of integrals, etc. Okay, please go through it. I hope you enjoy. We will meet again.